Hello everybody. In the last class we saw how an series RLC circuit would respond to an AC input signal, right? In today's class we are going to see how an parallel RLC, that is a resistance, inductor and capacitance connected in parallel, would respond to an AC signal applied across the parallel circuit. Okay, this is a circuit diagram which shows an AC signal is being applied. There is a resistance R, inductor L and capacitor C which are connected in parallel. So obviously, since they are connected in parallel, the applied voltage would be same across all the three components, whereas the current in these three will be different. Whereas in a series we saw that the same current would be flowing in all the three components and the voltage across them would be different. Here, since they are connected in parallel, the case is different. Here the voltage across all the three components would be same, whereas the current would differ depending on the impedance offered by individual elements, right? So this is the applied voltage is E max cos omega t. So the resultant current which will flow will not be in phase with the applied voltage. You can represent that by omega t minus del t. Had it been only a resistance, then it will be in phase. Had it been only an inductor, the current will lag by 90, and if it been had it been only a capacitor connected, then it would have the current would be leading the applied voltage by 90 degree. Now you have a combination of RLC, so we are assuming here it is going to lag by amount delta out here. Okay, so it could lag or it could lead depending on the relative strength of L and C that we will see here. So let's try and find. So this junction rule, which is I is equal to IR plus IL plus IC, that is going to hold good here also. That is Kirchhoff's current law, KCL at this node. If you see, this is the current which is coming from the source, and you have IR, IL and IC going out of these nodes. So I is equal to IR plus IL plus IC. So that would hold good out here also. So if I make a phasor diagram here, this is the voltage vector which is shown in the x-axis, applied voltage. The current in the resistor will be in phase, because you see the voltage and the current in the resistor will be in sync, and there will be no phase difference, okay, because it is going to follow Ohm's law, V is equal to IR. So IR is also shown which is going to be in phase with the applied voltage, and the same applied voltage is available across the inductor and the capacitor also. And we know in the case of inductor, the current is going to lag the applied voltage by 90 degree. So that is why this red line which is shown here, the inductor, which is shown pointing downwards, so IL. So in this particular example, we are assuming the inductor current is greater than the current in the capacitor, okay, and the capacitor current, we know that it is going to lead the applied voltage by 90 degree. So that is why it is shown in the upward direction. So if you have to find out the sum of these three currents, you have to take an you have to do vector addition, right? So initially we find out IL minus IC, that's the blue line, blue arrow which is pointing downwards, because we have assumed here in this case IL is greater than IC. So IL minus IC is this, and then you take the vector sum of these two, you will get I. Okay, so that I, if you see, that will be lagging from the applied voltage by a phase angle delta out here. Okay, so we need to find out this delta and I. So these are the equations. Now IR max is equal to E max divided by XR. XR is nothing but R. IL max is E max by XL. We know the impedance of an inductor is L omega, and similarly I max is E max divided by XC. X is 1 by C omega, so that's why this comes into the numerator as omega C. Okay, and also we know that if you see here, this is what? This is vector sum of this and this, right? So you can apply Pythagoras theorem. So I have I square max is equal to I square R plus IL minus IC max square. Okay, because if you see, this is vector addition, right? So this comes from the Pythagoras theorem. So now substituting the value of an IR max by E max by IR is equal to E max by R. So these values substituting, we get this equation, and I square is equal to E square. Okay, into 1 by r square plus 1 by L omega minus 1 by minus omega c the whole square. So this is the equation which we get out here. So if I have to write the impedance 1 by z, okay, 1 by z is not impedance, it is known as admittance. So 1 by z will be I max divided by E max. So 1 by r square, square root of 1 by r square. So this is coming from this equation. So I am bringing down this E max to the bottom and taking a root. So I am bringing, so this is 1 by z. Okay, 1 by z is known as the admittance. So this is the equation which we, so this is how, this is the equation which we need to follow to find out the impedance offered by a parallel RLC circuit. Okay, so I max again will be E divided by Z, right? So 1 by Z is this, so this comes in the numerator now here, E max. So this is the equation to find out what is I max out here, right? And what is delta? If you see here, opposite side, tan delta will be opposite side by an adjacent side, right? So opposite side is what? In this case IL minus IC, and this is going to be adjacent side is going to be IR. So so this is the equation, 1 by L omega minus XR. So this is the equation which we need to follow. So to find out what is the phase difference. So if you see both I and delta is a function of omega here. Okay, so unlike in DC circuits, in AC circuits the total impedance as well as the phase is dependent, is a frequency dependent component. It is not going to remain the same for all the frequencies. So you see there is a frequency omega available in the angular radian, omega is available in the I equation as well as in the phase angle equations. Okay, so that and then you can find out the currents in all the three. You can write it as an IL max into cos, because this is the current in the inductor is going to lag, whereas in the current in the capacitor is going to lead by. So this is going to be in phase. So this is going to be 0, this minus pi by 2 and pi by 2. So these are some of the these are the equations for the current out here. So let's take one problem. Here you will find E max, a 50 volt supply, this is maximum voltage which is applied across an RLC which is connected in parallel. So we need to find the amplitudes I1, I2 and I3 for two frequencies, 2 radians and 4 radians. So we will do the part B1 and part A you can do it yourself. Okay, so now first of all we need to find out, since it's an the impedances are frequency dependent, we need to find out what is the impedance offered at the particular given frequency. So here the angular frequency is given as 4 radians per second. Okay, if it is given in frequency, then you need to do 2 pi f, where if it is given in omega, you can directly write L omega here. So the resistance is 10 ohm. So the reactance will be of the inductor will be an L omega, which is again 10 ohms. We got 10, that is because 2.5 into 4, that is 10, and X is 1 by C omega. Omega is 4 and C is given as 0.1, so you get 2.5 ohm, right? So now we can find out the maximum currents in all the three elements, because the voltage is same across all the three. So they are all E max, all the three E max is 50, whereas this is 10, so you get 5, this is also 10, you get 5, and this is 2.5, so you get 20. Now we need to find out what is the current through this source. Okay, now if you see this current is this current flowing out here is nothing but the capacitance current. So that is 20 ampere, and the current in the inductor is nothing but 5 amperes. Now what would be the current out here in I2? If you see, it will be IL minus IC. Okay, because they are going to be 180 degree out of phase, these two currents. This is going to lead by lag from the applied voltage by 90 degree. This is going to lead the current by lead the voltage by 90 degree. So you have to take the difference of these two currents. You should not add it. So you have to be careful while doing these kind of problems. If I go back here, if you see IL and IC, they are in the opposite directions. Okay, so you have to take IL minus IC. So we are interested in only the magnitude part in this particular problem. So you take a mod of that. So you take a 20 and minus 5. So it gives 15 ampere out here. And then that is the current. And now this and this are going to be at 90 degree, right? If you see here, we have taken the difference out here. IR is the difference between the phase angle between these two is 90 degree. So that's why to compute the I max, we take a root of an IR square max and plus an I2 max square. So you get 15.8. So that is the max current which will be drawn from the phase. Okay, is it understood? Yeah, we'll move forward. Okay, we'll take one more example out here. Now in this, a resistor, a ideal capacitor and ideal inductor are connected in parallel to a source alternating voltage of 160 volt out here. Okay, so in these problems, see you have to be very careful with what is given in the question, whether it is peak value or it is the RMS value. So since it is given in this particular fashion, it means 160 is the RMS value and the frequency is given as 250 hertz and a current of 2 amperes flows through the resistor. Through this resistor 2 amperes flows, and then it says, and a current of 0.8 amperes flows through the inductor. Through the inductor also the current is given and the total current is given as 2.5. The total current here is going to be 2.5. So now we have to and we also have to presume that IC is greater than IL in this particular case. So we have to do that assumption also, and now find out rest of the parameters of this circuit. Okay, so if you see here, the voltage is given as 160 volt. Okay, that is the RMS voltage. Frequency is given as an 250 hertz. Okay, IR, the current through the resistor is given as 2 amperes. The current through the inductor is given here. The current through the capacitor is not given here, but in lieu of that, the total current which is being drawn from the source, that is given as 2.5 ampere here. Now we need to compute the values of R, C and L. Okay, so firstly R and L is going to be pretty easy because the voltage is known of 160, right? And then and the currents is also which is going through them is known, and also the frequency of operation. So R and L is going to be pretty easy. Then we need to compute what is the current going in capacitor C. Then once that is known, we can compute the value of the capacitance also. Okay, so to start with, resistance is, we know Ohm's law, so R is equal to V divided by R. So the value of R can be straight away computed. In case of inductor, we know it is L omega. So omega is 2 pi f and f is given here as 250. So using this formula, again V is 160, L is equal to 2 pi f L. So we get the value of the inductance also. Now the third thing is to find out, similarly, if you know the value of the IC which is flowing through the capacitor, then we can use this formula. V is equal to XC IC. XC is nothing but 1 by C omega. So so you write 1 by C omega. Omega is 2 pi f. So with that we can compute the value of C also. So now the problem remains to compute the value of IC, right? Now if you see in this particular circuit, okay, IC is greater than IL, so IC minus IL, so this will be like we saw in the previous problem, IC minus IL is going to be pointing upwards here, and then plus IR square, that will give I. Okay, so I square will be IC minus IL square plus IR square out here, right? Now we can expand that. Okay, because here if you see IC is not known, I is known, IL is known, IR square is known. So we have to expand this, okay, expand it, and then write it in an in terms of, this is a variable. So A square minus something A, because IC is a variable. So X square minus 2IL x, and then you have this constant. These are all known to us. So if you assume IC as a variable x, then you can write the equation is an 2a plus minus root of b square minus 4ac divided by 2a. This is the solving quadratic equation. So we can do that, right? Once we do that, we know the values of IL, which we have already computed. IL, IR and I has been given in the problem statement itself. These values have been given here. So putting those two values, you get an two values for an IC, right? So again here we have assumed that an IC is greater than IL, and it's in the positive, so it's going to be positive. So we are going to take this as a positive value. Okay, so this is the value which we are going to take. So once we have 2.3 amperes, okay, once we have we have computed the value of ICL, we can substitute it in this standard equation and get the value of the capacitance. Is it clear? Abhinav, are you following? Ananya? Okay.
Yes, sir.
Okay. Okay. Now, if you want to compute the power in RLC circuits, again for power, this is the standard equation which we saw in fact in all the AC circuits. That is going to remain the same here. That is the voltage taken from the source RMS into IRMS. IRMS and VRMS are the voltage of the source and current of the source, and then into cos phi, whereas phi is the difference between the applied voltage and the net current which is taken from the source out here, right? So that we can do. That is how the power is taken. So we'll see few problems maybe in the tutorials also. RL parallel circuit is just an special case of RLC circuit, you can say, where C is infinite, so you have removed C. So I and RL, so you have the voltage and the current. Voltage, applied voltage is shown in blue, V. IR, that is the current which flows into this resistance, that will be exactly in phase, given by V divided by R. Okay, whereas the current in the inductor will be 90° lagging with respect to the voltage. So in red it's shown out here. So if you see here, V, applied voltage V, IR and IL. Now if you take the vector sum of IR and IL, you will get the net current which will be drawn from the source out here. Alright, so that is the and then once you take the vector sum, the phase difference between the resultant will be given here. So that will be tan phi is equal to IL divided by IR. Okay, so that you can do that to compute the phase difference between the current and the voltage. So that is how this is then only a special case of parallel RLC circuit. Okay, so if you take an example out here, determine the phase angle ZT. ZT is the total impedance, IT is the we have to determine the phase angle, ZT total impedance, IT total current, IR the resistor current in the resistor, this is through the inductor, P in the parallel RLC circuit, okay, containing this is 1.4, this is the inductance given and this is the resistance given, 10 volt. Okay, when we say 10 volt, this is an RMS voltage, okay, operating at 4 kilohertz. So the frequency is also given. So XL will be L omega or 2 pi f and into L. So substituting that, 2 pi is 6.28 and then 4 is the 4 kilohertz, so 4 into 10 to the power of 3 and L is given as 1.4 millihenry, so 1.4 into 10 to the power of minus 3. So this is the total impedance offered by the XL or by the inductor. So the current will be V by R, for because in resistance it is resistance is 25 ohms, so you get 0.4. And to find out the current through the inductor, it will be V divided by XL. So we are writing a J in the JXL. Okay, that J indicates that the current is going to lag by 90°. So you have minus J 0. And 35.7 is this which we computed here. So you get this current which is going through L out here. right? If you see here, so now the total current will be vector sum of this, like this is the current through the through 0.4 is this current, right? And this is from the inductor. So 0.4 minus j into j 0.284. So if you have to find out the magnitude, so it will be root of 0.4 square plus 0.028 square. So you get 0.4. This we know how to convert it into a polar form. And this angle also is minus this divided by this. So that means it is going to this vector is the current is going to lag out here. Okay, so that is the reason the net current will be lagging the voltage. So minus 35.4. Okay, approximately 36 it's shown out here. So this is how we do the calculations. Okay, now the total impedance is an same thing, right? This is the current. So this is the total current in the phasor form. It's written out here, and the voltage which is applied is 10. So total voltage divided by total current will give you the impedance also, total impedance also, right? And then to find out the power dissipated by the circuit is V I into cos phi. So V is 10. And the current is this we found out the current to be 0.491, so 0.49 into cos 35.4. Okay, that is the phase difference here. So we get 4 watts. So is this understood, all of you? So how to compute the currents in an RL circuit and how to compute the total power. Okay, so we'll take on one more case. This is again an RC circuit, which is in this case the L has been removed. So we are assuming that in a parallel RLC circuit L is infinite. So you have only an ER and EC out here. So the capacitor current is, we know that, leads the voltage by 90 degree. Okay, so in the case of inductor it was lagging the applied voltage by 90. Whereas here it is going to lead the applied voltage by 90 degree, right? So again this is the vector triangle which we show IR, which is in phase with the applied voltage, whereas IC, which is going to lead the applied voltage by 90 degree, and you take the vector sum of these two things, you will get the total. Again the phase angle will be given by IC divided by IR. Right, so and the total current will be given by by Pythagoras theorem again out here. I total will be root of IR square plus IC square. So this is one example also has been given here. It says this is 8 and 12. Find out what is the total current out here. Okay, so it will root of A square plus 12 square. So you get 14.4 out here. So okay, this is one more example out given here, where 120 volt has been applied. This is 10 ohms, and here straight away the impedance is given here, XC. Okay, so you have to be careful. Okay, so once it says omega out here, okay, it means already this 60 hertz has been taken care of in this problem. So be extremely careful with this. Don't multiply on again 20 with 2 pi f. Okay, since the unit is given as 20 ohms, that means at this particular frequency of interest it is giving 20 ohms. Okay, so don't multiply again, don't assume this to be 20 farad or microfarad and do mistake in your exams. See, when it's given 20 ohms, okay, straight away you can take that as to be the total impedance in ohms. So IR is 12 and IC is again 120 by 6. Okay, again this I have been repeating this many times. See, it's given like this, it means it's an RMS voltage. So you get 12 amps RMS voltage and 6 amps RMS voltage. Because in the exam, maybe in the final or here, I might give a problem like this, but then finally I might ask you to tell what is the max current which is flowing in this resistance in this particular case. Okay, so in that, if you have to find out the max current, you will have to multiply the RMS voltage by root 2. Okay, so now you can find out a total current, which is a square root of 12 square plus 6 square. So you get here, right? And then tan inverse, the phase angle also is IC divided by IR. So you get this value, right? So this is written in the vector notation. this is written in the rectangular notation. Okay. So if you see here, capacitance, when we write, the whole thing is 90° out of phase than the applied voltage. So it is all imaginary, and since it's leading, it is plus J out here. Whereas in the resistance, it is in phase, so this J component is 0 out here, right? So this is one example of a parallel RLC circuit. So we'll take on a few more problems in the next tutorial, and in the next class we'll see something a little more interesting about RLC circuits, which is known as resonance. Okay, after that we move on to 3-phase circuits. Okay, so that's all for today.